Hey everyone, welcome to Rasayan Academy once again. So here we are with another video on the metal oxidizing agents, and today we are going to discuss lead tetraacetate and cerric ammonium nitrate, and then we also see some examples of dihydroxylation reaction. Okay, so first we move onwards to this lead tetraacetate, guys. Now this is a very important organic oxidizing agent. See, lead tetraacetate with the formula like this is mostly soluble in the organic solvent. So it is very popular for doing the diol cleavage. But just like this, the periodic acid is also very popular in doing the diol cleavage, right? So what is the difference between both of these? Both of them are doing the diol cleavage, vicinal diol cleavage like this to give you two different carbonyl compounds depending on what kind of diol you have taken. If there was a hydrogen present over here, it's going to give you two aldehydes. Otherwise, if there was the R group, it will give you two ketones, right? So the difference in these two, lead tetraacetate and periodic acid, is only of the solvent. Okay, that is LTA or lead tetraacetate is used for glycols that have low solubility in the aqueous media. For those who are not soluble or having a very low solubility in water, for those we are going to take lead tetraacetate, and the periodic acid will be taken in the aqueous solution, which means the diols which are soluble in water will be cleaved by the periodic acid, and it does the same job. Okay, you must have also seen this in the carbohydrates. When you are studying carbohydrate, it is very extensively used, okay, for the diol cleavage. Now, also, this is the most popular reaction of lead tetraacetate, in which it is going to react with the diol, vicinal diol, and it's going to eliminate 2 moles of acetic acid. It's going to give you this acetate ester, cyclic ester, 5-membered ring, and that is going to break up in this way to give you two different kind of aldehydes. Okay. Now, second is, if let's say we are taking the lead tetraacetate in the presence of LiCl, a little reagent can make a very big difference. So you see, the presence of lithium chloride, the product is going to be a corresponding chloride. You are not going to get any aldehyde, you are going to get a chloride. So let's say there was this carbonyl compound over here, this one, this is the acid, for example. So acid might do decarboxylation in the presence of lead tetraacetate, but here in the presence of LiCl, this is going to give you a corresponding chloride. We'll see more examples of such type. See, what you can do is, when you are having alpha hydroxycarboxylic acids, they are going to undergo oxidative decarboxylation to give ketone. Now this has been asked in your CSIR net exam once. It's obviously an old question, right? But it has been asked in the exam, and see what's happening. Alpha hydroxycarboxylic acid, that on the same carbon you have COH and the OH group. How does it work? It is not forming a 5-membered ring by the loss of 2 acetate molecules. No, it is removing 1 acetate from the lead tetraacetate, and the oxygen of the acid gets connected to lead. Now the oxygen, the OH bond, breaks apart in such a way that there is decarboxylation minus CO2, as well as elimination of lead diacetate, as well as elimination of CH3COOH present over here. Alright, this whole group is going to eliminate like this. Where is this CH3COH coming from? It's coming from one of the acetate groups which has eliminated. And decarboxylation ke baad you are going to get the ketone over here. So alpha hydroxy carboxylic acids after oxidative decarboxylation will give you ketone in this particular reaction. Okay, very important one. Next, let's see. Now what do we have here? We have a gamma keto carboxylic acid. So you see, this is alpha, this is beta, and this is gamma. That is on the 1, 2, 3, third position, you are going to have a keto group. So gamma ketocarboxylic acid preferentially yields alpha beta unsaturated ketone, because there is a possibility that after the decarboxylation you can create a double bond over here. So how does this reaction go through in the presence of lead tetraacetate and copper acetate? Okay, so see the hydrogen. See, first of all, just like this one, the lead tetraacetate is going to remove an acetate group. It connects with the oxygen of the carboxylate group, and followed by that, since this proton is acidic, it is connected on the it's present on the alpha carbon. It is already acidic and it's going to leave along with the CO2. This is the mechanism, and this is how it gives you alpha beta unsaturated ketone. So two very important type of reactions other than just diol cleavage. Okay. Also, just like manganese triacetate, which we have covered in the last video, it was also doing the acetylation on the alpha position. It is doing the same thing and goes through the same mechanism. That is, we start with the, let's say we start with a simple cyclic ketone over here. It is in the presence of acidic conditions, it is going to give you enol. Okay, it is absolutely going to, even if a little bit, but it is going to give you some enol, which is going to first get attacked by the lead in such a way such that it's going to give you the enol radical. It's going to give you enol radical, which on reaction with another acetyl radical in the presence of lead triacetate is going to give you the alpha acylation. So you see what just happened in the presence of enol. The lead tetraacetate is not giving out an acetate minus charge. No, it is not giving out this. It is giving away lead triacetate and one acetate radical, which is going to pick out a hydrogen from here, one hydrogen radical, which leaves you with an enol radical, to which this attaches on the carbon, not directly on the oxygen but on the carbon. So very, very important. This is just like the manganese triacetate that we have studied. Okay, it's very, very simple. Moving onwards, look at this example, another important example. What do we have? We have 1,2-dicarboxylic acid, isn't it? We have 1,2-dicarboxylic acid. What does it do in the presence of LTA? So it is undergoing decarboxylation to give you an alkene. So if it is present, see, if the 1,2-diols are present, they are going to break and give you aldehyde. If 1,2-dicarboxylic acid is present, they are going to break and give you an alkene, and these are all the side products. There will be two CO2 elimination, and I hope that you understand how this happens. Once again, this is going to break in radical form, take out a hydrogen, and that gives you one acetic acid molecule, and the rest of the molecule is going to fall apart in this way and fragmentation, okay, to give you alkene. Very, very important. Okay, so we see the similar thing over here. See guys, again LTA we have taken, we have an ester in this molecule, we have a protected alcohol over here which is not going to react, then we have a diol. So for diol we know what's going to happen. The diol is going to break down in the presence of LTA and basic conditions minus 40 degrees centigrade to give you two different aldehydes. This one is an aldehyde over here, and the other part is also going to break down into formaldehyde. Okay. Similarly, you know, there could be a question based on the rate of reaction, rate of diol cleavage, for example. And there has been a question in the previous years based on the per iodic acid. The same question could be framed for the lead tetraacetate. That is, out of let's say 3 or 4 examples which are given, which one is going to give you the slowest diol cleavage? Definitely the one where the two OH groups that you have, if the two OH groups are trans to each other, that reaction is going to be slowest. Why? Because when you are forming the ester, when you are forming the 5-membered ring, of lead tetraacetate when it is connecting to the diol, that's only a 5-member ring and it will not prefer to be trans because it's a small ring. So the same we see over here, if the OH are trans and they are fixed, rigid, for example, the reaction will be very slow, and if they are cis and it is also fixed, the reaction will be very fast. Okay, they are obviously giving you the same product, but the rate of reaction is going to vary. So trans is going to give you slow reaction, and cis diol will absolutely give you a faster reaction. Okay, so these are some of the applications of the lead tetraacetate. Now we move onwards to cerric ammonium nitrate. All right, it is very popular. It has similar uses just like DDQ and stuff. We will also talk about DDQ, but in the non-metal oxidizing agents. Right? So cerium is present in +4 oxidation state. Let's find out how. Because the nitrate NO3 minus, there are 6 of the nitrates present, right? And if the cerium is coordinating to 6 nitrate, there is 2 minus charge remaining, which means that the cerium is only +4. That's why it is having a residual charge of 2 minus. Often a question is asked about this, that what is the coordination number of cerium over here? The coordination number of cerium is not 6, even though it looks like the nitrates are 6, so it should be 6, but it is 12. The coordination number of cerium is 12. Why? Because the nitrate, very rarely this happens, that any ligand like this, which usually works as a monodentate ligand, would behave as a bidentate ligand. That depends on the size of the metal. If the metal is too small, for example, all the 3D series, these are small metals, right? So if cerium size is big, and what happens is, if the size of the metal is big, then there is very less steric repulsion, or the 4-membered ring is also going to be stable if the size of the metal is big. If it is too small, that there is going to be more steric hindrance within the ring, within the chelate ring which forms, right? So cerium being the perfect size for the nitrate to behave as a bidentate ligand, this is how the complex actually is. So the coordination number of cerium is 12. It is surrounded by 12 sides, and also the oxidation state of cerium is +4. Now cerium +4 only carries out one electron oxidation to give you cerium +3. Okay, and yeah, it's written over here, only one electron oxidizing agent it is. It is useful as an oxidant for many functional groups like alcohol, phenol, and ether. Okay, also especially for benzylic CH bonds, especially it is going to behave as an oxidizing agent for the benzylic CH bonds. As an example, you see this one. That is, the benzylic alcohol is converted to 94%, you are getting the yield, it is converted to an aldehyde by the removal of one of these hydrogens and oxidation. Okay, so this is one role of cerric ammonium nitrate, oxidation of benzylic alcohol or normal alcohol to aldehyde. Alkenes would undergo dinitroxylation, and the product is going to be solvent dependent, whether you are having the dinitroxylated product, or let's say you are having the acetylene after hydrolysis, or the diol, right? Depends on the solvent. Quinones are produced from catechols and hydroquinones. So what are catechols? Catechols are 1,2-diols, and hydroquinones are 1,4-diols, like this. So from here you are getting the exact reaction just like DDQ, that is, they are going to convert into the benzoquinone form, that is the double bond O, oxidized form. We will see an example of that as well. Let's first move onwards to this one. So what is this? It's a 1,4-diol, 1,4-diol molecule, and because the conformation is locked, it is fixed close to each other. In such a conformation, can के साथ में sodium bromate use हुआ है. Why the bromate is used? For the reoxidation of cerric +3 to +4. So whenever there is one more oxidant present with any reagent, most of the times it's working as a co-catalyst, या co-oxidant. Okay, right. So what happens is, first of all, in the 1,4-diol, which is rigid molecule, one of the alcohol is getting converted to CHO like this, and the other alcohol is going to attack over it to give you 1, 2, 3, 4, 5-membered ring. That 5-membered ring that you get is not lactone directly, it is first going to be a lactol. What is a lactol? This is a lactol. Okay, that is, it is having the acetyl bond, hemiacetal bond like this. It's going to be the lactol, which is further oxidized to the lactone. So this is how the cerric ammonium nitrate is also used. Also, the most important application which is similar to DDQ is the formation of, see, you can take a hydroquinol form or you can take a substituted hydroquinol form as well. All of these will be oxidized into the benzoquinone. So from the catechol or substituted catechol molecule, you are going to get this type of a quinone system. Alright, and from the 1,4-hydroquinone or substituted molecule, you are going to get the benzoquinone form. Alright, it is exactly similar to DDQ. We will do the DDQ in the non-metal based oxidizing agents. Okay, now let's move onwards very quickly to the dihydroxylation part. So basically guys, see, here you see 3 different examples. One is the Woodward and Prevost conditions, which are using silver carboxylate and the alkaline KMnO4 and the osmium tetraoxide. So there are 3 important reagents for dihydroxylation as well. We have already covered this in a name reaction video where we have also talked about examples. So I wish all of you go through the video to do the proper mechanism, because here we are only talking about the reaction and the products. So if you have started with a cis alkene, as you see over here, this cis alkene, while reacting with iodine and any silver carboxylate salt, whether it is benzoate or acetate, whatever it is, in the presence of a non-polar solvent where there is no water, is going to give you a trans product, and that also you are still getting the trans dicarboxylate like this. After hydrolysis, you are going to get a trans diol in this way. Also, if the same cis alkene is treated with iodine and again silver carboxylate salt of any acid, that in the presence of water as a solvent. So the difference of water you see when water is taken as a solvent, you will first get, in the first step you are going to get something like this. It is not a diol yet, but it is an alcohol and a acetyl group, which on hydrolysis is going to give you a cis diol. Okay, so you can check out the whole mechanism in the Woodward and Prevost video. Okay, moving onwards, alkaline KMnO4 also gives you syn addition just like osmium tetraoxide, and we have also done this before in the previous slides कि alkaline KMnO4 क्या करता है, alkene को oxidize करता है to give you a cis diol, and it is syn addition reaction, that is both of the oxygens will attach on the same side. Okay, now there is a common confusion कि अगर हमारे पास cis alkene है तो cis diol मिलेगा, but if you are having a trans alkene, for example, if you are having a trans alkene like this, how is the product going to look like? Okay, so the oxidation has actually taken place from the same side. So the diol is going to look like this. Okay, it is still a trans diol, it's not a cis diol. And when you are rotating from this bond, one of the alcohol is above and the other one is below. ठीक है, तो अब ये ट्रांस डायोल बना है क्योंकि alkene ही ट्रांस था, but the addition is syn addition, that is the addition is on the same side. That's why we have to mention syn and anti-addition like that. Next important reagent for dihydroxylation is osmium tetraoxide. It is again very popular for doing the dihydroxylation to the alkene. What happens is the osmium tetraoxide is going to add to the double bond to the alkene in this way, and it's going to give you an intermediate like this. You know, it is giving you the osmate ester. It is very popular बहुत ही ज्यादा पॉपुलर है ये. अब इसका ऑक्सीडेशन स्टेट हो गया है +6. इट वॉज +8 बिफोर. And after this, it's going to cleave the bonds. It's going to undergo hydrolysis to give you two OH groups over here. So rather it becomes H2OSO4, जिसमें भी इसका oxidation state +6 ही रह जाएगा. So because the osmium reduces, we are going to use a co-oxidant and convert it back to osmium tetraoxide. अब ये जो co-oxidant है वो बहुत सारे हो सकते हैं. It could be N-methyl morpholine oxide, or it could be sodium perchlorate, potassium perchlorate, silver perchlorate, barium perchlorate, or it could also be potassium ferricyanide, in which the iron is present in +3 oxidation state. That is also possible. All of these are used as co-oxidants. ठीक है. Now this is all very simple. If we talk about the stereochemistry of this reaction, or if we talk about the directing property, this is one very important aspect. So you see that the alcohol which is present over here, how is it going to direct the osmium tetraoxide? Alcohols are usually supposed to carry out hydrogen bonding with the reagent, and that's why we expect that it is going to give this one as the major product. ठीक है, क्योंकि इसका बहुत एक अच्छा एक प्रोटॉन है यहाँ पे विच इज वेरी एसिडिक. इट कैन डू हाइड्रोजन बॉन्डिंग. कैसे कर सकता है देखो, थियोरेटिकली अगर बोले तो it can do a hydrogen bonding like this, that there is the double bond and it is going to form the osmate ester like this. Alright, so this hydrogen can be pulling the osmate or osmium tetraoxide on the same side. लेकिन ऐसा होता नहीं है. हम सोच रहे हैं major, but it is not the major one, it is the minor one. Why the hydrogen bonding is not taking place? And in the first case it is not taking place. Why? In the first one you see that the diol is formed, but it is on the opposite side of the OH. और ये major product है 12:1. और दूसरे केस में when I am taking TMEDA, which is a chelating agent, in that particular case I am getting the diol same side of OH as the major product 1:9. So why is there the difference? I want to discuss with you. That is, if you are taking a simple molecule like OSO4 in this way, then the osmium is there in the +8 oxidation state and it is so electron deficient that it is pulling away electron density from all the oxygen. तो ये जितने भी ऑक्सीजन यहाँ पे लगे हुए हैं, इनमें से सब में से अगर इलेक्ट्रॉन डेंसिटी ऑक्सीजन के पास चली जाए ऑक्सीजन से, then what will happen? Then these oxygen are themselves delta positive and it will not attract a delta positive like a proton. तो इसीलिए ये हाइड्रोजन बॉन्डिंग नहीं होती है यहाँ पे. There is no hydrogen bonding with simple osmium tetraoxide. That's why you don't have a directed product. Rather ये OH क्या कर रहा है? ये bulkiness का काम कर रहा है. It's providing bulk, steric hindrance, and that's why the diol formation goes below the plane in the first case. In the second case, what we have is, you see, when the osmium is bound with TMEDA, what is that? Tetramethyl ethylene diamine. In this way. Now this is a chelating agent. ऐसे करके ये osmium को chelation कर रहा है, right? And that's why it is releasing electron density from osmium to these oxygens, and now they are going to be delta negative in nature, which is going to attract delta positive. तो अब ये hydrogen bonding करेगा, okay, and now it is going to direct the diol formation on the same side of OH, and that's why this is the major product. I hope you understand this. Now this next one is a very beautiful example of asymmetric dihydroxylation, जो हमारी next video में cover होगा, अभी नहीं होगा. I'm just showing this to you that this is how we do the asymmetric synthesis, and there is a big ligand which we have to see what are the ligands and how it is giving you the diol. All right. So ये बहुत एक अच्छा सा एग्जाम्पल है जो हम नेक्स्ट वीडियो में कंटिन्यू करेंगे, so that we understand dihydroxylation in the asymmetric way. Okay, acha, chalo, let's move onwards to the next example. Now you see, you have a OBN group and the alkene. Now it is OBN, protected alcohol, it is not an alcohol itself. So there is proof in Caruthers and in different books, there is proof that if you are having the OH, because it is small in nature, it can do the directing property. It is possible to be able to get the directed product in the presence of OH when we apply TMEDA. लेकिन इसके अलावा जो ये ग्रुप्स है OMe, OAC, OBN, all of these groups, even if you apply TMEDA, which is the agent for chelation, तब भी कोई direction नहीं होगा. First of all, they don't have the OH bond. Secondly, they are also bulky. So what we see is in the presence of this particular group, the diol will be formation on the below side. So you see 7.6 greater is to 1 because here the diol formation is taking place below the plane. Okay, that is the osmate ester which will be formed below the plane like this. ठीक है, नीचे से बन रहा है यहाँ पे below the plane से, and that's why giving you the below the plane diol. But after the bond rotation, one of them goes up. तो ऐसा नहीं है कि ये trans है, ये cis alkene है, just representation is different. So let me show you how it is. You are going to get a product in this way. OH and OH. Now if I just rotate this bond, I'm going to get this. ये OH ऊपर चला जाएगा. So the product formation is from below the plane. Above the plane product formation, that is attacking on the same side as OBN, is not possible. तो ये जो OBN है जो directly connected है यहाँ पे, इसके opposite में ही attack होना पड़ेगा. Now, what are some of the oxidizing agents for the carbon-carbon double bond? We have seen chromium compounds, not just carbon-carbon double bonds, for more molecules. We have seen chromium compounds, manganese compounds. We have also seen, we are going to see per acid, osmium tetraoxide and ozone. अच्छा, ozone का भी बहुत simple सा reaction होता है. We will see that in the non-metal oxidizing agents along with DMSO and so on. ठीक है? Okay. Some high oxidation state halides and nitrogen or sulfur compounds. We will see the sulfur compound DMSO because ये usually आता है exam में. Okay. Now I want to also share this example with you all क्योंकि मुझे ये याद आ रहा है, ये example आपके exam में पूछा गया था. That is, I am having this kind of an alkene and from here I want to generate two different types of a diol. So one of the diol was like this. I have the OH. Both of these were cis diol, right? दोनों ही diol cis diol है. तो इस टाइप से अगर एक मॉलिक्यूल फ्रेम क्वेश्चन फ्रेम किया जाए तो how are we going to answer this particular question? Both of these are syn diols. How are we going to prepare them? So just try to think by yourself. मैं तो हुई आंसर करने के लिए. So ये देखो, first of all, अगर हम osmium tetraoxide और NMO से oxidation कराते हैं, this is one method. Or if we take alkaline KMNO4, they are both going to form the osmate and the manganate ester, which is going to be from the less hindered side. तो अगर मैं ester बनाऊं, osmate ester बनाते हैं, so that is going to be from the less hindered side, that is from below the plane. It's going to look like this. And after hydrolysis, it's going to give you this product. So the first one is very easy. Either you're taking osmium tetraoxide and oxidizing agent or KMNO4 alkaline. That's both going to give you this molecule. This one is a little bit tricky because what we have to do is we have to think about this. It is from the Woodward cis dihydroxylation. How we know that? Because in the Woodward reaction, you are first doing the addition of iodine. पहले हम iodine का addition करते हैं जो कि definitely it's going to be on the less hindered side. अब यहाँ less hindered side कौन है? Below the plane. Because above the plane there are these two methyl groups. So below the plane is the less hindered side, which is going to be attacked by acetate in the presence of silver, so that this bond is going to break such that it gives you an acetate over here. ऑल्दो इट्स बल्की, लेकिन ये ऊपर से ही अटैक करेगा बिकॉज दैट इज ओनली बैक साइड अटैक, and then it is going to do NGP reaction to go through this. तो after NGP हमें क्या मिलने वाला है, हमें ये मॉलिक्यूल मिलने वाला है एसिटेट, OCCH3 and one more oxygen over here. After hydrolysis you are going to get this diol over here. So these are two different reactions. ये आपके एग्जाम में आ चुके हैं, बहुत ही पुराना क्वेश्चन है, but nonetheless it is important and relevant because it tells us about the stereochemistry of these reactions. Okay, so yes guys, I will see you all in another such video. Please like the video, also subscribe to the channel, और अगर आपको कोई भी suggestion है तो आप comment section में डाल सकते हो. I will see you all soon. Take care all of you.